Okay, section 12.1 begins chapter 12 for us, and chapter 12 is multiple integrals. So it's this idea of integrating over areas to get volumes, or integrating over volumes to get, well, sort of a hypervolume. We'll mostly focus on the plane for the first few sections, and then we'll move our way into triple integrals towards the latter half of chapter 12. So to begin with, we need to recall that we're always looking at functions f from the plane r squared onto the real line r. Remember that the graph of such a function is in three-dimensional space, r2 cross r. And what we're interested in doing is integrating the function f over a region. Well, in this case, a rectangular region. So section 12.1 keeps everything simple. We're going to integrate over rectangles in the plane. Of course, we know that we could integrate over more interesting regions or more elaborate regions than just a rectangle. We can draw any, versus a rectangle, we can draw any kind of region in the plane. But for now, we're just going to stick with rectangles. Okay, so a rectangle is defined as all the points x, y in the plane r squared, such that x is between a and b and y is between c and d, and a, b, c, and d are just real numbers. This is a breakdown of that notation that we might see. An interval cross an interval is literally the rectangle formed by those two intervals in the plane. Now, for the purposes of setting things up, we'll assume that f of x, y is greater than or equal to 0 on this rectangle r that we're given. And if that's the case, we'll essentially be calculating the volume underneath this function, or between this function and the xy plane. So what we did in the past, if we look down below, is we had a function f from r to r, from the real line r and onto the real line r, the x-axis onto the y-axis. And what I've drawn below is an x-axis, and I haven't drawn the y-axis, and that's on purpose because what we're just looking at here is the domain of this function, f of x equals y. Okay, so the way we would split this up in the past is if we wanted to find the area underneath a curve, perhaps there was some curve above this, then we would split the interval up and we'd approximate it with rectangles and so on to calculate the area under the rectangles, and that would approximate the area underneath the curve. Now, the analogous situation for a function from the plane into the real line would be to look at each of these sub-rectangles of this overall rectangle R, and that's actually a three-dimensional entity here, and it's a cubic, or a rectangular solid that stands up from the plane, and the height of that solid is the value of the function f of x, y at some point within there. That's what we would use to approximate it, at least. So now, instead of having approximating rectangles, we have approximating rectangular solids. So to go back to some of the details of these situations, we recall that for a function from r to r, our single variable function, we'd calculate delta x. Delta x would be the step size that we want to make between each of these interval lengths. Of course, that didn't always have to be the same length. It just turns out that if we use the same length, it simplifies our processes, especially our approximation techniques. And then also recall that we could use right endpoint, so all of these endpoints, versus left endpoint of each interval to approximate the function f for its value for the height of each rectangle that would occur over these subintervals. Okay, there was also the option to use the midpoint of each of these intervals. Okay, now we have something very similar for the rectangular situation. Here what we'll do is we'll have delta A. Delta A doesn't have to be a bunch of rectangles. It doesn't have to be the same for every one of these subrectangles. So all these subrectangles can have different areas and different sizes. But just to simplify our algorithms and the way we handle this, we'll probably assume for the most part that they're always the same. In fact, I think all exercises that we'll see will use the same subrectangle areas. Now that's formed by, we'll need a little bit of information here, delta x times delta y. So the way that we split up the x-axis times the way that we split up the y-axis for our rectangle R gives us our delta A. Delta A now is an area. We'll have to note that that's the case. So we split up the y-axis into n subrectangles, 0 to n here, and then the x-axis into m subintervals, and that'll form n times m subrectangles. So there are m times n subrectangles of area delta A. And a very similar thing to what we did in single variable calculus happens here. For each of those areas, the volume that's contained in one of these little subrectangles, we'll say that maybe this would be a point here in this one, and then v sub I for this subrectangle, j based on both what x coordinate we're at and what y coordinate we're at. Okay, I being x, j being the y subindex, and it's going to be equal to f of xi, yi, the point that we choose within that subrectangle, times delta A. Okay, so that's how we would get the volume of this. F of xi, yi represents the height of that rectangular solid that's standing up above this, and that's what we've used to approximate the volume in that region, in that subregion. Okay, so that will be, and if we do that and add up all of those volumes, then we'll get all of the volume, or an approximation of the volume that's underneath this the surface that's over this region. Okay, now the decision is also a little bit up for grabs, right? We can use top right endpoints of each of these subrectangles as follows, finishing out the rest of this with these red dots in the top right endpoints, coming to here to finish, and down there lastly. There could also be bottom left or top left. We have a bunch of different choices now just because of the fact that we're in the plane instead of being on the real line. So top left would be these, bottom left, bottom right, you could imagine. Probably one of the more accurate ones, though we won't go into an error-bound analysis, would be midpoints, right? We found that midpoint was one of the most accurate ways to approximate areas under curves for functions of single variables, and that more or less carries over to multi-dimensional, or functions of two variables, multivariable functions. So we'll see the rules for any of those situations. Some will be straightforward. The midpoint rule is given to us in some detail in a box or formula, but the others can be just inferred from the situation. So now, of course, if we're going to calculate the exact volume of a surface that's over this region here. Now, remember, the surface could be any shape. Right here, I've drawn a sort of a parabolic shape. It's a terrible looking parabolic shape over the top of that. But we can imagine that the cap of a sphere or cap of a paraboloid or anything, or cone, could be sitting over the top of that region, and we would want to calculate the volume between that region and the xy plane and whatever the surface is above it, that bounds it from above. So if we wanted to find the exact volume, we would shrink each of these squares until they're smaller and smaller, and we take many, many more squares. That's a limiting process of shrinking the areas and increasing the number of squares that we use. And so what we'll do is we'll run the limit as delta x, delta y goes to 0. In other words, the limit as delta a goes to 0, and f of xi, y, j. And that will give us essentially our Riemann sum, which you'll see on the next page. So we'll define the double integral of f over the rectangle R. It's double because we have to add up over the xi, f of xi's, and then over the f of yj's, right? As ordered pairs like this. So we've got to add everything up over the y's, over the x's, and then we want to limit the delta xi's and delta yj's to go to 0. So we're producing more and more rectangles to fill in this subrectangles to fill in that region. So we eventually reach infinitely many subrectangles of infinitesimal size or infinitesimal area, and we'll have dA is that infinitesimal area, and we get our actual exact volume from this. So it's the limit of a Riemann sum, and of course that right-hand side of this is called a Riemann sum. If such a limit exists, if this limit exists, the function f is said to be integrable. So that's another term that we see on this page. And there's one last note that will, it'll be helpful, and it won't really block our techniques of proving these things. Were we to look into the proof, if we just assume that delta Aij has the same area for all ij. Okay, so in other words, we divide the rectangle R into equal subrectangles, subrectangles of equal areas. Okay, so if the function f of xy is greater than or equal to 0 over the region R that we're integrating it on, then we'll interpret this integral as the volume of this solid bounded by f from above and the plane xy below, or the region R in the plane xy below. Okay, so let's see some approximation techniques first, and then we'll move into actual full integrals of things. So first and foremost, they ask us to estimate the volume of the solid that lies below the surface z equals xy. So f of xy equals xy over the region ordered pairs xy such that x ranges from 0 to 6, y ranges from 0 to 4. So to get started with these, and as you learn what you're doing, it's a good idea to map this out. This is our plane from 0 to 6 marked off on the x-axis, from 0 to 4 marked off on the y-axis, and then we've subdivided it accordingly. 2, 4, and 6, 4, and 2. Well, we're not sure how we need to subdivide it yet, so let's read further in the problem before I get to that. But we have our xy plane here, and they say to use a Riemann sum with m equals 3, n equals 2, a regular partition. In other words, all the subrectangles have the same area, and sample points to be the upper right corner of each square. Okay, so if that's the case, we need to figure out what is what here. So to calculate delta x, which we don't actually see here, it's given implicitly, but we'll just note that delta x is calculated by 6 minus 0 over m, which is 3 in this case, which is 2 now, and delta y is 4 minus 0, its interval length, divided by 2 as well. It's also 2. This number is this one, this number is this one, and that's how we come out to a subrectangle area of 4. Okay, so now to pick our x sub i's, well, we know that we have a unit step length of 2 for delta x, and so as we've hashed out these values here, we're going from 0 to 6, so we step from 0 to 2 to 4 to 6, and same thing along the y-axis from 0 to 2 to 4 till we've met both of our lengths. We've gone from 0 to 6 and from 0 to 4. And then we subdivide, right? We know that at each of our delta x's, it's a length 2. So at for every length of 2 along the x-axis starting at 0, we put a subdivision, and that's these lines right here, these vertical lines along the x-axis. We're intersecting the x-axis. And then we'll do the same thing along the y-axis, 0 to 2, and then to 4. We put horizontal lines to subdivide here. So our region R, the rectangle that we're integrating over, is actually this larger rectangle here in red. Okay, and what we've done is we've split it into these 6 subregions. There should be no question about that. 3 times 2 is 6, and that'll tell us the number of subregions we should have. Okay, each of those subregions has area 4, as we've seen. Now the next thing we need to do is come up with the points. Well, we're using the top right point for each of these squares. So this handles that. And the points we've listed off to the side here are exactly those that are circled. You can check that. And now we're ready to estimate our volume underneath this integral, or underneath this curve on this region R. So here's our double summation or double Riemann sum, and f of xi, yj. So these are, each of our points will be plugged in there for I equals 1 up to 2, and I equals 1 up to 3, and j equals 1 up to 2. And that's multiplied by delta A, which will be 4. We'll see below. So here's 4. And then f of xi, yj is xi times yj. That's from the definition of f, or z equals xy. And now it's just a matter of, well, we factored the 4 out just to simplify things. This is a constant times a sum times a term in a sum. So it's times every one of these terms. And this is x1 times y1, x1 times y2, x2 times y1, x2 times y2, so on to x3 times y1 and x3 times y2. Add all those up, multiply by 4, and we have a volume approximation of 288. Okay, so that's very much like what we've done in single variable calculus, only now our domain is the plane, and we have a little bit more to think about and be careful of in terms of splitting things up and calculating sub areas and the points that we're going to plug in. So let's do the same thing, but with the midpoint rule. Now, there's a little bit of definition here for the midpoint rule. Remember that xi bar, yj bar will be the midpoints of each subinterval. So that would put us effectively in the middle of each subrectangle, and we'll see that down below in the example. And yeah, that's all we really need to know from that. Of course, finding the midpoint is a matter of, we'll see how to calculate that in a moment. So same function, z equals xy. So in other words, f of xy equals x times y. Same region R, same rectangle R. X is between 0 and 6, y is between 0 and 4. So of course, this is our overall rectangle R right here. Okay, we divided it into 6 equal subrectangles. Again, well, they tell us m equals 3, n equals 2, so we're going to have 6, like we said there. And also, we have, we're using equal area subrectangles as well. Careful to do that. If they don't tell us to do an even partition, then we should just do one anyway. In fact, with the midpoint rule, it probably should be assumed that we'll do an equal partition, or a regular partition is the other term for that. So just always assume a regular partition unless told otherwise. Now, for the midpoints, it's easy to spot the midpoints of each of these. To calculate them is a little bit more. So let's look at least the first one. So I'm thinking of this one here. This is from 0 to 2 on the x-axis, from 0 to 2 on the y-axis. So x1 bar, the midpoint of the x-axis for this subrectangle is x1 plus x0, which is 2 plus 0 divided by 2. That's this here, and that gives us a value of 1. And of course, reasoning this out, and if we draw things like this every time and the numbers are friendly enough, it's pretty easy to realize that this point occurs at x equals 1, and then doing something similar with the y values, 2 plus 0 over 2 gives us 1 here, and we have the midpoint for that one as well. Carrying that out for each one of these now, or realizing that we can just add delta x and delta y to each of these. Delta x again is 2 and delta y is also 2. Of course, that can be calculated off to the side somewhere if we'd like. And we just add 2 to 1 to get 3, and then 2 to 3 to get 5. We had 2 to 1 to get 3, and that would make up all of our x bar and y bar coordinates. Or we can look at it in the picture and reason it out. The formulas are there if the numbers aren't very friendly. It's going to be quite possible that we'll see fractions show up in these as well. So we've listed all the midpoints that we're going to use for all of these rectangles, subrectangles, the values of them. Then the formula is essentially the same, only now we're using xi bar, yj bar. We should be clear that there should be a bar above there so we know we're using these midpoint values. Okay, of course, and 4 times the sum of all those products gives us 144 as an approximation of our volume in this case. So a little bit different than the 288 we saw before, but we're using different points, and with a volume like this, things can probably really get away from us if we're not using an accurate approximation rule. Of course, if we wanted to be more accurate, we'd take more rectangles and we'd make them smaller, and we'd do the same thing, only that's going to cost us quite a bit in these calculations because it's going to cause even more computations to need to take place. Of course, we've got tools for this. We know through the limiting process that what we arrive at is the integral that we're familiar with. And we already have Fubini's theorem to tell us how to handle that. So if f is continuous, and moreover, f doesn't even have to be completely continuous. It can have finitely many discontinuities. As long as these integrals exist, this will still be true. But if we're going to integrate over the region R, the rectangle R, the function f of x, y, then we have this iterated integral here that we just integrate f of x, y with respect to dy from c to d. And then the result of that function, we integrate with respect to x from a to b. Okay? And Fubini's theorem tells us that, as well as we can switch the order if we like. We can integrate with respect to x from a to b, and then the result of that will integrate with respect to y from c to d. These are called iterated integrals because we do one integral and then the other one. Now, provided our function f is continuous or only has finitely many discontinuities, which will be pretty much everything we ever look at in this course, we can swap the orders of these things. And well, also the integrals need to exist. So we will keep an eye on whether or not one of these integrals is broken or doesn't exist for some reason over the region that we're talking about. So what are we given below? We're asked to evaluate this double integral over the region R. Here's our function in our integrand. And the region R is the rectangle 0 to 1 in x, -3 to 3 in y. And we've demonstrated Fubini's theorem a couple different ways here. We're integrating from 0 to 1, then from first -3 to 3, then 0 to 1, dy dx. Or we could choose to go the other way, integrate with respect to x first, then y, flipping our integrals, our limits of integration, swapping them over. And it looks like we've decided to go with the second. When we're dealing with rectangles, it's probably not really crucial which order we integrate with respect to. It won't be too much more difficult than that. And section 12.2, picking the order will be key to success in a problem sometimes. So just having a look at what happens here. What we've done is, in this step, we've decided to integrate with respect to x first. And we realize we have x over x squared plus 1. So that is a good candidate for a u substitution since x, remember y squared is just a constant in this, since x is related to the derivative of x squared plus 1. So u will be x squared plus 1, du is 2x dx. Solving for x dx, because that actually shows up in our integrand, we have 1/2 du. Change our limits of integration, don't forget to do that, and the result of it is the line below. So with our changed limits of integration from 1 to 2 and our substitution for u and x dx, we have du over u. This 1/2 was part of this 1/2 right here. And y squared is a constant with respect to u. So we're really just integrating this portion for now, right, inside the other integral. So the result of the integral of du over u is the natural log of u. The integral of 1 over u is natural log of u, or the antiderivative of 1 over u is natural log of u. And then it's natural log of u from 1 to 2. We only plug these values into the function of u that we have here. So that's natural log of 2 minus the natural log of 1, which is 0. And now we have a constant of the natural log of 2 inside this integral. It's this line right here. So we factor that out as well as the 1/2. It's already been factored out. And we have natural log of 2 over 2, and we need to integrate from -3 to 3 y squared with respect to y. This is a standard Calc 1 integral. When we're done with this, we end up with 9 natural log of 2. Okay, so it's like two integrals sort of wrapped around each other, convoluted with each other, in which you still operate in a normal single variable way. You just have to hold one variable constant versus another as you work your way through. So let's see another one. Find the volume of the solid that lies under the hyperbolic paraboloid. Z equals 3y squared minus x squared plus 2. Remember that this is our function f of x, y, right? Sort of interchangeable, like y and f of x used to be in Calc 1. We're using the rectangle notation here, which is the same as saying this below, right? So either way we want to see that, I've just pointed it out in this case just so we're not confused about what this means. It means x ranges from -1 to 1 and y ranges from 1 to 2. Of course, that gives us our limits of integration that we see here. And working our way through this, we can pick either direction. We can integrate with respect to y first or with respect to x first. Again, with rectangles, it really doesn't matter. So we'll do this one with respect to y first, it seems. So each of these functions is integrated with respect to y. So 3y squared becomes y cubed. This is a constant with respect to y, so it's been collected as 2 minus x squared times y. So that had a, originally a power of y to the 0 there, and the power rule says raise that to y to the 1. And that's what we've got in this case. Evaluate from 1 to 2 for our y values. And what we see within this outer dx integral, within it we see y cubed, 2 cubed minus 1 cubed, and then plus y equals 2 minus y equals 1 times 2 minus x squared. Okay, the result of that is some constants times x. So we have 9 minus x squared dx in our integrand. This again is a Calc 1 integral, and the result of it is 52 over 3, carrying out the usual steps. Properties of double integrals. Now, of course, these can be used for shortcuts or to handle what seems to be intractable integrals, something that doesn't seem to be something that we can't quite integrate with the techniques that we know. Most notably, something like symmetry could help out in these situations. So we'd want to pay attention to that if possible. Getting a bound on an integral is another thing, right? So if f of xy is greater than or equal to some function k of xy for all xy in the region we're integrating over, then of course the integral of this function is going to be greater than or equal to the integral of that function, just like for single variable functions and their integrals as well. Okay, probably one of the most important is this. If f of xy can be factored into two functions, g of x times h of y, in other words, everything involving x factored into one term times everything involving y factored into another term, then we can split those integrals up and integrate each on their own as single variable integrals and multiply the result. That's a nice thing to have lying around in case things work out that way. We can split double integrals over sums. That shouldn't be any surprise. That comes from the linearity of the limit and the summations of the double integral definition. And we can factor out a constant L to the front of an integral. Again, that comes from linearity of the limit and the summation from the double integral definition. Okay, so that covers all of these properties. Let's see which one of these is useful down below. We're asked to calculate the iterated integral from 1 to 3 on the x-axis, and then from 1 to 5 on the y-axis, just reading this as we have it, of the function natural log y over xy. We can factor these two functions apart from each other. In fact, I'll write that off to the side somewhere. We have that natural log y over xy is equal to 1 over x times natural log of y over y. This won't always be possible. Don't force it. If two things don't factor from each other like this, there's no reason to force it. You're just going to have to leave them nested. Don't get a wrong answer because you wanted things to factor out like this. Not all integrals will do this. or not all double integrals will do this. This one does. So what we do is we factor everything involving x to here, and then everything involving y to here. And notice that we've brought the integrals of integration along the x-axis, 1, 3, and the dx with this function 1 over x, as expected, and the same thing for y and y variables. And from here, these are just two standard integrals from Calc 2, or really just Calc 1 in this case, since it's just a u substitution. We know that 1 over x has an antiderivative of natural log of x. Evaluating from 1 to 3, we'll finish that one off. And we know that, well, a u substitution of u equals natural log of y, because we recognize that 1 over y, which is this part of that integrand, is the derivative of natural log of y. So du is 1 over y dy, and we end up with u du in this integral. We've changed the limits of integration since u is equal to the natural log of y now. Integrate that u to get 1/2 u squared from 0 to natural log of 5. Carry out the rest of these details, multiplying these two integral values together at the end. And this is our final answer here. Okay, so that is double integrals over rectangular regions with first some approximations. Then we use Fubini's theorem to be able to calculate iterated integrals and see that we can swap the order of integration if we need to or would like to. And then we've seen a couple properties of integrals, so we can split up sums of integrals. We can factor out constants in double integrals, and we can bound integrals with the integral of a function that's less than or greater than a function we might be interested in. Most importantly, though, we can factor two integrals apart if we can write them as a function g of x times a function h of y and simplify our work to evaluate that. So in section 12.2, we'll be doing double integrals over more general regions. Things will get a little bit more delicate and interesting there.